topic is asymmetric diameters, and I'm now in my PhD. This is a joint work with my supervisors, René Brandenberg and Bernardo González-Merino. So the topic has unfortunately nothing to do with topology. This is something about convex geometry, and so I try to keep it basic and understandable. So feel free to stop me when there is something that I didn't explain. How does it work? This one? So let's start with some basic definitions. First of all, we need the circumradius. So that's something we know from the high school. So we have a polytope, here is a hexagon, and we have a circle, and we want to find the circumradius of the hexagon with respect to this Euclidean ball. How do we do it? We inscribe this hexagon in the ball, and after find the radius of the ball. So this definition of the circumradius can be generalized for any two convex bodies. So instead of this circle, you can take any convex body, and this will be the definition. So the circumradius of the convex body K with respect to C. When I say convex body, I mean convex and compact set in Rn. Then we take the body K, translate the body C so that K will be inscribed in C, and the rescalation factor will be this circumradius. Now, why is it interesting to consider such a thing like a circumradius? There is an application in the information theory. So in essence, call it hypothetical imaging. So here is a case that is used in the medicine. Here you see human food with some internal wounds, some hematome, and what we want to know is how deep is it located, which form it has, which shape, the depth, maybe the concentration of blood in one place, and all these characteristics. So how do we do it? We want to consider our wound as a convex body, and we want to slice it into layers. So what we do, we take a direction, take the hyperplanes that has this direction as orthonormal, and then slice it up. And in each of this hyperplane, we consider the image. And taking all the slices together, we have the full hyperspherical imaging. What is the problem about this? We want the algorithm that works fast and accurate. So what we want to know is not to consider the wound itself, but we want to consider some points, the finite amount of points, and take the convex hull of it. So we consider not the convex body, but the simplex. So a polytope that will be inscribed in our convex body. And this is the idea why we use the circumradius, the diameter.
It doesn't look like very convex.
Well, this we can imagine. The connectivity we need. So, another example is about the cheese. So the same thing we do, forget about the balls. We want to know the concentration of protein in the cheese, and then we apply the same tactic. So the next definition we need is a diameter. Again, return to the example with the hexagon and the circle. When we consider the diameter of this hexagon with a circle, we take any 2 points. It makes sense to consider the extreme points of the hexagon, so the vertices. And after we take these 2 points and consider the circumradius of these 2 points. So what does it mean? We consider some 2 points of this body, and then find the smallest rescalation of the ball, so that this body will be inscribed in the ball. And the radius, 2 times this radius, will be our diameter. Here, if you see, the diameter is equal to 2 times the circumradius. But in a general case, that's not true, because if you remember, we can consider not just the ball, but any convex body. So we can check, for example, the hexagon, inscribe it in a triangle, and then this will be not true. The next thing we need is a gauge function. The gauge function, that is also called the asymmetric norm, is defined like this. So this is again our hexagon, now we fix the center, and we want to find the distance from x to this hexagon. And this will be the gauge function of x with respect to the c. So what we do, we rescale our hexagon so that this point will belong to it. And the smallest rescalation factor will be our gauge function. So intuitively, this measures like the distance from a point to a body. Or you can take 2 points and then you can measure the distance between 2 points with respect to a body.
The point is 0 and you choose a arbitrary point.
Yeah, we fix the center, we need it.
So this also depends on the
Sure, yes. And that's a very good comment. So in the gauge function, we care about the center, while, for example, in the diameter or in the circumradius, you see we allow the translation. So we don't care about the center.
So it differs from the usual distance from the point to a set.
Yes. So we know that the diameter is defined like 2 times the maximum circumradius of 2 points. But if we are in the symmetric case, symmetric we mean that if we flip our body, then it will stay the same. So it's point symmetric. And it happens that then the diameter is the maximum distance between 2 points with respect to this body. But unluckily, if we take the body as symmetry, for example a triangle, then these 2 things are not equal anymore. And we have examples when, for example, the distance can be arbitrarily small, while the circumradius will be fixed.
Excuse me, in your picture, what is K and what is C?
So in my picture, always K I take this hexagon, and C is the circle. So it's usually the ball.
Any circle, you have 2.
Yeah, so I mean, this one was from the circumradius, and here we choose 2 points, like this point and this point, and taking the circumradius, so we inscribe only these 2 points in our circle.
So in principle, K and C are
2 convex bodies, yes.
Yeah. But the distance, for example, you can use the Gromov-Hausdorff distance.
Yes, sure, you can use it. And so we have this definition of the normal diameter, and we see that intuitively the diameter is the largest distance between 2 points, and we see that they are not equal. So what we do is we define this to be a symmetric diameter. So here's the maximum distance between 2 points with respect to the C. We define this as a symmetric diameter. And this is used in different literature. In physics, so different points of view of different people use one diameter and the other, and it is interesting to relate them to have some common thing. So, but one can think that if you consider the maximum distance, it is not accurate for some problems. And instead of taking the maximum distance from one to the other, you can take the average of them. And this is why we take the arithmetic mean of these 2 gauge functions. So we have now 2 different asymmetric diameters and the ultrasymmetric diameters. And now we want to relate them. In order to do this, we need some more details, and one of them is the Minkowski sum. The Minkowski sum is nothing different like the vector sum. So you take any point of K, any point of C, and add them. So here's an example. You have a yellow triangle, a blue triangle, and if you take the sum, then you have this nice regular hexagon. Okay, so let's return to our diameters. We have the diameters that is defined as the maximal distance from one point to the other. We have the other one that is the maximum arithmetic mean of these distances, and we have the old one. The old one was the 2 times the circumradius of 2 points. But what is interesting, if you remember, is that when we have C to be symmetric, this one was just the maximal gauge function. And if we take instead of C the arithmetic mean of the bodies itself, then it happens that their diameter stays equal. So the diameter can be represented as the maximum of the gauge function with respect to another body that is c minus c half. Unfortunately, if we consider this thing, the gauge function of c minus c half, it is impossible to present it as a function of the gauge functions of c or minus c. So we have to find something different to compare them. But let's check some obvious relations. So first of all, we see that the normal arithmetic diameter is bigger than the arithmetic asymmetric diameter, because here we take just the maximum, here we have the average. And also the normal diameter is smaller than both of them. And here I have an example where we can see that there is an example when they are equal and when they are strictly smaller. So here we have C to be this circle, and let's say K2 is this segment. When we consider the normal diameter, you see that it is the same as like the maximum distance between 2 points. So all of the 3 diameters for this body K2 with respect to C are equal. So we have here all equalities. But if you take the other segment K1, in order to find K, we take this point and this point, and after we shift our C and we scale it smaller, such that this segment will be inscribed in C. So you see that in this example, the diameter is strictly smaller than both of them. And even more, there are cases when the center is badly located, then it's really, really smaller. So here is a triangle to be the body C, and a K is this segment. And we choose the center of the body C be close to this vertex. Then, in order to find this diameter, what we do, we take our C, we rescale it such that this facet, this edge, will be coincide with the segment. And you see the rescalation factor will be really, really small. And if we take this, the center be arbitrarily close to the vertex, we get that the diameter will be also really small. That's the problem about the diameter and the center. So we must fix the center, otherwise we can get bad examples when it tends to 0.
Is it essential in the previous that the small interrow is parallel to the...
This one?
Yeah.
Yes, because in this case, when we take this triangle and we shift such that this one will coincide with this segment. And in this case, you can really take the factor will be like the old age to the new one. So this was done intentionally, sure. So how do we fix the center so that we will not get a problem about the diameter? Here is the Minkowski symmetry. What we do is, this is some measure about how asymmetric is the body. So we say that the ball is symmetric and the triangle is the most asymmetric. But all the bodies in between can be characterized by this S of K. How we do it? We take our body K, let's say this is K. We flip it around, so this will be minus K. And then we enlarge it so that the old body K will be in the new body. And this factor, the rescalation factor, will be our Minkowski symmetry. And for the triangle, if you see this is an old triangle, this is a new triangle, and you need exactly this factor 2. So it is known that the symmetry lies between 1 and n, where n is a dimension. And we have that 1 is for the ball, and n is for the triangle. And also, we can fix the center of the symmetry. That is called the Minkowski center. And now you will see if we fix the center, we have no problem about the diameter tending to 0 or other ugly cases. But let's now continue with some other definitions. The definition is the polar body. So we take the set of all points x such that the scalar product with every point in K will be less or 1. So this means if this is a 0, and we take this point, for example, on the boundary, and let's say that the distance from 0 to this point will be 1, then this point will also belong to the polar body. But if we take something here, for example, let's say the distance from 0 to this point is a, where a is less than 1, then it will go into this point that is larger. And you see if you had a polytope, the polar body of a polytope will be another polytope. And what is interesting about the polar body is how it works. So you see, if the distance, so the gauge function from this point was 1, it stays 1. When it was a, it goes to 1 over a. So this is something like a generalization of the operation taking the inverse. And using this knowledge, we can now define the means of...
Can you show once more?
Yes.
So the polar should include K. K0 should include...
That's not always the case.
Not
Not always. Because if you have a point that the gauge function was greater than 1, then taking the inverse of it, it will be 1 over a, and it will be small. And then this all vertex will be out of it. So let's introduce the means of the convex bodies. So first of all, remember just the means of numbers, like say real numbers. We have the minimum of two numbers, we have the harmonic mean of two numbers, arithmetic mean, and the maximum of two numbers. And we can generalize this for convex bodies. So let's have a look. Here we have the section of C and minus C. This can be seen as the generalization of the minimum of points A and minus A. The same here, C minus C half, can be seen as some number A minus A half. Here, the union corresponds to the maximum, but because we want to have everything convex, we take the convex hull of the union. And also this thing, this is the harmonic mean of the convex bodies. Here we have the polar, this corresponds like 1 over A. And if you check, this can be really directed from the definition of the harmonic mean of the numbers. And here is an example how it works for the triangle, so for simplex in dimension 2. Let's say this is our triangle, C. Then to take minus C, we just flip it over, and we have this triangle. Then take the section. The section will be this, the smallest hexagon inside. Taking the convex hull will be the biggest hexagon, and now the harmonic mean will be this black hexagon, and the arithmetic mean will be the orange one. And we see that all of them are one into the other. So we have the containment chain in one direction, but we also need, in order to use this for the diameters, to have the inverse chain. So we want to know the factor that we need, for example, for the convex hull to be contained in this section. And in order to do this, we will now use our Minkowski asymmetry factor. So we showed that if we want to have the reverse chain, we have to multiply with this factor, 2s plus 1. And then we have the inverse chain, and all of this body will be optimal contained in each other. Optimal means that you cannot find a bigger escalation factor so that it will be contained. And we connected all of these means. So now that we have the normal chain, the inverse chain, let's this apply to our diameters. Here is the chain, the section, harmonic mean, and again the section. Then, taking the gauge functions with respect to these three bodies, we have some inequality for the gauge functions. And it's funny that the harmonic mean of the convex bodies corresponds to arithmetic mean of the gauge function. So if we have this inequality, taking maximum of two sides leads to the diameters. This means we bounded the normal diameter to the arithmetic asymmetric diameter by 1 and the vector that is coming from here. Now we have the second chain about the intersection and the arithmetic mean. We do the same. We take the gauge function with respect to these bodies, then we have the equality like this. It's 1 to s, 1 plus s over half, taking in the maximum on both sides, and we get the relation of the asymmetric diameter to the diameter itself. So here's the result on one slide. So the asymmetric diameter is greater than the arithmetic asymmetric diameter and is bounded by this factor, and this factor is always smaller. So s is smaller than n, and this is smaller than 2n over n plus 1, and here is the same. And actually, this was everything I wanted to tell you. Thank you.
Okay. Any questions from the audience?
Nobody do these results in practical computation.
We don't really do practical computation, so we work in different areas connected with the symmetry. One of the things we would like to do is using the idea of the means to get some results on the problem of the Banach-Mazur compactum.
But no, because at the beginning you showed the pictures.
Oh, you want
Very
computation?
practical to make some. You don't do this.
Oh, you mean this one?
Yes, exactly.
So we don't do it, but some people from the Department of the Information Theory, they use this result to do this kind of imaging. And this is really used in practice in medicine.
So you mean the result that you mentioned, this inequality?
The result itself is not used now at the moment. No.
So they use just these numbers,
The idea-
statistical numbers of
So-
the diameter or something.
Yes, the idea is you have something like this, and you don't want to consider all of it. You want to take some points on the boundary that will have all your information needed, and then apply these points, you have some simplex. And for this simplex, they just apply the idea of slicing it and imaging on all of them. And then in order to get this simplex, we need to inscribe it in our convex body. And this is exactly the same radius. Okay?
Any further questions? Okay, if that's not the case, then let's thank the speaker.